Okay, so in class we said that by definition a series is absolutely convergent if its absolute value, the series in absolute value form, is convergent. If the absolute value version is divergent but the series itself is convergent, then the series is conditionally convergent. Let's break this up so that it makes sense and you can digest it better. So here's one thing it says. It says a series is absolutely convergent if its absolute value series, if the corresponding series with all positive terms, converges. This is one thing it says. For example, let's look at this series and see how this makes sense, this one statement only by itself. So if I look at this series, of course it's an alternating series, and I can force the terms to become positive by taking out the negative and taking the absolute value of everything. So I look at it like this, with absolute values, and I basically get this new series that's different from the original one because it only has positive terms. And we know that this guy is a convergent p-series. So we can conclude that this original series I started with absolutely converges because when I took its absolute values, it actually ended up being with a series that converges. So it basically said this right here. I look at the series and then I just pretend all the terms are positive, and if I pretend all the terms are positive and that thing converges, then I can automatically conclude, well, that's absolutely convergent. Now let's look at the second thing that this definition included, the statement about conditionally convergent that confused some of you. Basically says a series is conditionally convergent, or just convergent, we call it, if its absolute value series, this guy, if I force all the terms to be positive, diverges, but the original one, the one that was untouched, converges. So let's look at this example. This is the original series. We're going to go and look at its corresponding absolute value series. So we're going to force all the terms to become positive. When we do that, we get this guy over here. And we know that that guy is a divergent p-series because it's the harmonic series. So we cannot say that this absolutely converges because when we took its absolute values, it did not converge, it actually diverged. So now I got to go look at the original series and see what happens there. If it doesn't absolutely converge, I can go back and resort to the original series. So unlike the previous example when I was done after I took the absolute value and said, oh, it absolutely converges, here, if I'm looking at it, I conclude that this does not have absolute convergence. So I asked, does it maybe then converge at least conditionally? To answer that, I have to go and look at the original series. So go back to the original series and see what happens there. So here I am back at the original series, and the original series clearly is an alternating series. So I can look at my Bn and see what happens. And we've shown this before, so I won't go through the full proof of it. 1 over n, Bn are continuously decreasing, and also the limit of 1 over n goes to 0. So it satisfies both conditions of AST. Therefore, this original guy converges by AST. And we can conclude conditional convergence because when we went and tried to check the absolute values, that guy did not converge, but the original one converged, so it has conditional convergence. So let's go back and review. If the absolute value series converges, you have absolute convergence. If the absolute value series does not have convergence, it diverges like it did here, but the original guy that you resorted back to converged, then you have conditional convergence. Now another thing we talked about was that absolute convergence implies conditional convergence, but not the other way around. We said if something absolutely converges, you get conditional convergence for free. In other words, over here, when I showed absolute convergence, that automatically means this series converges in the sense that we used to call convergence before. And you can show that just doing the AST test on this as well. So absolute convergence in one sense is important because sometimes for a series it's much easier to just look at positive terms and analyze it. And if you can show absolute convergence, then you've automatically shown convergence. So why does this happen? So if a series is absolutely convergent, then it is automatically convergent. So let's think about this. When you force the terms of a series to be positive, in a sense it makes it more difficult for the series to converge, because if you have both positive and negative terms in a series, that may help you out because things can cancel. When you force everything to be positive, you sort of lose any negative terms that you would have had in that series, and that prevents any cancellation that may occur, and the partial sums could keep getting bigger and bigger and blowing up because you don't have any negative terms anymore. You forced everything to be positive. So if you can show absolute convergence, then that's really stronger, and in a sense, this other guy may come there for free. So we think it may seem reasonable that an absolutely convergent series is also conditionally convergent, or just convergent as we call them, and as we've called them up to this point. So this absolute convergence implying conditional convergence kind of seems like, okay, it may work. If I have shown the difficult one where everything is positive and yet converging, then the other one where I even have some negatives helping me out should still apply. So let's go and formally show this implication, this thing that says absolute convergence implies conditional convergence. So let's suppose that AN is absolutely convergent. If that's the case, we know that this has to hold by definition of absolute convergence. So we know that this guy convergence just because the series is absolutely convergent. So notice what happens when I create this inequality. If I take A sub n, just general term of this series, and take the absolute value of A sub n also, I can have two things happen. If the term is positive, its absolute value is also going to be positive, so I'm going to get double the value of that term. So I'm going to get twice what I had if A sub n is positive. If A sub n is negative, well, A sub n will be negative, its absolute value will be positive, and the two guys are going to cancel each other out and go to 0. So I have this inequality that should hold. A sub n would be positive, the absolute value would be positive, hence it's just going to get doubled. So this guy will have to be less than or equal to this. If A sub n happens to be a negative term, then with its absolute value combined, they must cancel each other out and go to 0. So this inequality will hold for sure for any general term of the series. So now, since we have that the A sub n in absolute value converges, because that was our given fact, we also know that double the absolute value of A sub n must also converge, because that's just a multiple of a convergent series. So this must also converge. So then we can conclude that by the comparison test, then I must also have this series that converges. Why does that happen? Because this series over here was convergent because of this guy being convergent, and all the terms of this series are always going to be less than the terms of this series. So this right here helps me determine that by a comparison test, this other new series that we just made up, absolute value, this also converges. Now we're going to go and we'll make up our A sub n from the previous pieces and show that it also has to converge. I'm going to come up with this series that I know from here by the comparison test was converging. We also know that this was converging because it was a given fact, because the series was absolutely convergent, this had to be true and be convergent. Now what happens when I look at it like this? I have two series that were both convergent, so when I look at them in this form using the properties of series, this also converges. And that leads me to, well, these guys are going to go away. This must also be convergent. So we formally showed the stronger implication that we keep talking about. That if you, what our intuition tells us, that if you have absolute convergence, in the process you're automatically going to get convergence or conditional convergence. And using a comparison test and properties of series, we showed that you can sort of build up A sub n being a convergent series just by knowing the fact that this statement had to be true, and this had to be true due to being an absolutely convergent series. So that's the proof of why that is going to happen. Let's look at an example where we ask, does the series converge absolutely, does it converge conditionally, or just simply converge, or does it diverge? So how are you going to, if you're specifically asked for that question, this is what I suggest you do. The order in which you check things may make it easier. If you're asked that question, the very first thing you should do is check the absolute value series. If it converges, you can stop, you're done, you showed absolute convergence. If A sub n and absolute value diverges, you're not done, you got to go back to the original series and check to see what happens there. Once you're back in the original series, if you can show that it converges, you're done, you've shown conditional convergence. If it diverges, you're done, you've shown that the whole thing diverges, period. So let's answer this question for this guy, for the series given. First thing we're going to do is take its absolute values. When I take its absolute value, so I look at the absolute value series, this is the guy I get. This makes me think I should try some form of a comparison test. So I'm going to say this reminds me of n over n cubed, which is 1 over n squared, and I know that creates a convergent p-series. And we know that n over n cubed plus 2 is always going to be less than n over n cubed because this denominator is going to be bigger always. But that guy is just this, so we can conclude that by the comparison test, this series converges. But since we had taken its absolute values and showed it for the absolute value, we have actually shown absolute convergence. So, the original series I started with absolutely converges because the absolute value version of it converged. Let's analyze the same thing for this guy. I'm going to check its absolute value version. That gets me to this guy, and now I need to analyze this. Again, it reminds me of maybe a comparison test or a limit comparison test. So I'm going to guess my Bn to be this, and that corresponding series is a divergent series because it's a multiple of the harmonic series. Now the terms of this series are always going to be bigger than the terms of the harmonic series, because notice on the left the denominator is actually smaller than the denominator on this side. So, by CT or the comparison test, this guy in absolute value diverges, which means I cannot stop, I need to keep going back to the original series. So no absolute convergence, we're going to go try checking conditional convergence on the original series. This original guy is just an alternating series with Bn just positive terms being this guy. Bn is decreasing always because if I look at the n plus first term, put in n plus 1 for your n, these guys will always be less than this guy because the denominator on the left is bigger. Also, the limit of 1 over 2n minus 1 goes to 0. So, both criteria of the alternating series test are satisfied. So therefore, the series converges conditionally. The absolute value version of it did not converge, however, the original series did converge, so it conditionally converges. Keep in mind that the ratio and root tests actually help us with deciding absolute convergence, which automatically implies conditional convergence and also divergence. So they're really useful in answering these questions.